You've heard it. We've all heard it. That constant rumbling roar from a construction site. It's the sound of our cities being built, and a lot of that noise comes from the humble cement mixer. For decades, it's been an absolute workhorse, but honestly, it hasn't really changed much. Well, that's over. Behind the scenes, there's a quiet revolution happening, and it's turning this brute force machine into a masterpiece of smart engineering. And this quote, this says it all. I want you to just think about the sheer absurdity of this for a moment. We're firing up a massive diesel engine, an engine built to haul 40 tons down a highway, and we're letting it idle for hours just to do a job that needs less than 10% of its power. From an engineering standpoint, it's the definition of overkill. It's inefficient, it's wasteful, and it's the core problem we had to solve. So let's put it side by side. On the left, you've got the old way, the roaring dinosaur, one giant engine trying to do two very different jobs, and frankly, doing both of them poorly. You're getting maybe 30 to 40% energy efficiency. But on the right, you see the new way, the right power for the right job. It's silent, it's clean on site, and look at that efficiency number. We're talking over 90%. This isn't just a minor tweak. It is a fundamental reinvention of the machine. Okay, so to really appreciate the solution, we first have to dig a little deeper into the problem. Let's break down exactly why the traditional mixer is such a noisy, inefficient giant, and what's forcing the industry to finally change its ways. So here's the deal. The core problem is that you have this big diesel engine that has to stay on, idling for hours and hours at the job site, guzzling fuel and making a ton of noise, all just to keep that drum slowly turning. Now, for a long time, that was just accepted. But now you have powerful catalysts for change, like EU regulations demanding a massive 45% CO2 cut by 2030. And that creates this fantastic engineering challenge, really the million-dollar question. How on earth do you build one single vehicle that needs to be a long-haul highway cruiser 1 minute and a silent, zero-emission stationary machine the next?
So, how do you solve a puzzle like that? Well, the answer isn't a bigger engine. It's not about more brute force. It's about being smarter. So let's get into the new blueprint, which completely rethinks the architecture of this vehicle from the ground up. The first piece of this puzzle is what we call a P2 hybrid architecture. Now, what does that mean? Well, just think of it as ultimate flexibility. We strategically sandwich a powerful electric motor right between the diesel engine and the gearbox. And by doing that, the truck suddenly gets all these new superpowers. It can cruise silently through a city on pure electric power. It can use both the engine and the motor together for a massive power boost going up a hill. Or it can even use the diesel engine as a generator while driving on the highway to top up its own battery. It's incredibly versatile. Okay, now this is the masterstroke. It's called the electric power takeoff, or ePTO. Instead of using complex, leaky hydraulics to steal power from the main engine, we give the mixer drum its very own dedicated electric motor. And here's the game-changing part. We completely decouple the drum from the engine. This means the truck can pull up to a site, shut down its main diesel engine completely, and the mixer just keeps turning, silently, on pure battery power. The two jobs are finally separate and optimized.
Now, a leap forward like this doesn't just happen with a sketch on a napkin. It takes rigorous, methodical systems engineering. As a systems architect, this is the playbook. It all starts with the SOR, the Statement of Requirements. This is our Bible, defining every single thing the truck must do. Then we create a function tree, which breaks down every goal into specific tasks for the hardware and software. From there, we design the master system architecture. And, absolutely critically, from day one, we build in the Functional Safety Requirements, or FSR. This process is how you turn a brilliant idea into a buildable, reliable reality.
All right, let's dive into the heart of the machine. To really understand how all these pieces work together, I'm going to use a really simple analogy that I think makes it all click. We're going to talk about brawn versus brains.
It's actually pretty elegant when you see it this way. The whole system has two parallel electrical circuits. First, you've got the brawn. This is the big, powerful 400-volt high-voltage system. Its only job is to do the heavy lifting, powering the huge electric motor to drive the truck and the other motor to spin that heavy drum of concrete. Then you have the brains. This is the familiar low-power 24-volt system. It's the command center. It doesn't move anything. It just thinks, senses, and sends orders to the brawn. And this is how those two systems talk to each other. Let's focus on the two key parts of the brains. First, you've got the CAN bus. You can think of this as the truck's digital nervous system, sending tiny 24-volt signals back and forth with precise commands like add more torque or spin at this exact speed. But second, and this is non-negotiable, you have the high voltage interlock loop, or HVIL. Think of it as a constant 24-volt tripwire that runs through every single high voltage connector. If any one of them comes even slightly loose, that 24-volt signal is broken, and it instantly, and I mean instantly, cuts all 400 volts of power. Okay, but here's where the design goes from just being smart to being truly brilliant. That electric motor for the drum, the ePTO, it's not just spinning the concrete, it's feeling it. By measuring the tiny changes in electrical torque needed to turn that drum, the system can digitally monitor the concrete's consistency, what we call its slump, in real time. All of a sudden, this isn't just a dumb truck anymore. It's a mobile quality control laboratory on wheels, ensuring a perfect pour every single time. Now, whenever you're dealing with this much electrical power and this much moving mass, safety has to be the absolute #1 priority. And I'm not talking about a checklist you fill out at the end. I'm talking about a rigorous discipline of engineering for the absolute worst-case scenario from the very beginning. This is the question. This is the one that every single systems architect has to be able to answer. With 400 volts coursing through the chassis and a multi-ton drum spinning just a few feet away from people, what happens when something inevitably goes wrong? To answer that, we don't guess. We perform a hazard analysis and risk assessment, or a HARA. We systematically imagine every terrible thing that could happen, and we assign it a safety rating, called an ASCL. And look at these. A worker is inside the drum for maintenance, and it starts up by accident. That's ASCL D, the highest risk level there is. The high voltage system fails, and the entire truck's body becomes live. Also ASCL D. These aren't just academic exercises. These readings dictate that our safety systems have to be practically foolproof. And here's the golden rule of functional safety. For the highest risk levels, like ASCL D, you can never, ever rely on software alone. Safety has to be physically built into the hardware. So what does that look like? It means that maintenance hatch has a physical interlock switch, part of that HVIL circuit we talked about. You open the hatch, you physically break the circuit, and the battery is disconnected. It means the motor controller has 2 lockstep processors inside, 2 brains constantly checking each other's math. If there's any disagreement or any critical fault, the entire high voltage system is shut down and made safe in under 1/10 of a second. That's a fortress. So, we've gone through the problem, the blueprint, the tech, and the safety. After all of that incredible engineering work, what's the actual payoff? What does this mean in the real world, on the construction site, and on the balance sheet? Let's start with the big one, 50%. That's the potential reduction in on-site fuel consumption by simply shutting off that big diesel engine. Instead of letting it idle, a fleet owner can cut their fuel bill at the construction site in half. Over the lifetime of a truck, that is a staggering amount of money saved and a huge reduction in the total cost of ownership. And then there's the quiet part of this quiet revolution. A traditional mixer is screaming at over 85 decibels. That's like having a freight train parked outside your window. The new system, in its silent ePTO mode, is under 72 decibels. That's closer to the sound of a normal conversation. For workers on site, and for everyone living and working nearby, that is a massive, massive improvement in quality of life. So when you add it all up, what you have here is a classic triple win. It's a win for the business, with dramatically lower costs. It's a win for our cities, with less noise and less air pollution. And it's a win for the construction industry itself, which now gets a higher quality, more consistent product every single time, thanks to that precise electronic control. In the end, this story is about so much more than just concrete. What we're really looking at is a blueprint. A blueprint for taking a traditionally dumb, brute force machine and making it intelligent, efficient, and incredibly safe. And it really leaves you with one fascinating question to think about. If we can do all this for a cement mixer, what's the next machine that's ready for its own quiet revolution?